Hello everyone, in this video you learn about Fourier transform and absolute value of complex numbers. So let's first check how humans hear sound. In physics, a wave is a disturbance that travels through space. If a human speaks, the voice generates sound waves traveling through the air, and when these waves hit the eardrum, then it generates vibrations, and these vibrations pass through the cochlea, which transform these vibrations into electrical signals, and these electrical signals are sent to the human brains, and the humans interpret these electrical signals. So what you just saw is the process of converting the analog signal into the digital signal. So um, you can do it with Python and given a signal um, like this. So if this sound file is saved in the path somewhere, and you can load it with librosa, the load function. And if you wanna see the amplitudes for the given time domain, then you can use wave show and pass the signal and the sampling rate. And if you check the signal shape, then it is 66,150. And if you check the elements up to 3 elements, then it looks like this. And you may wonder why the signal is of shape 66,150. The Librosoda load returns signal values for the sampling rate, and the sampling rate is about how you split 1 second. For example, sampling rate of 162 will give 162 times 3, which is 486, because the duration is 3 seconds. And the end of the audio can be set with the duration parameter. So let's um, do this with me. And first you gotta download the data with this link. And actually, if you go to this site, then you can download it by pressing this button. And I have already downloaded. So if you go to the downloads folder, and if you go into this folder, then here go inside again, and let's um, just open anything, and here let's pass this path, and I'll use anaconda. Let's set the path, um, paste, and you need to give this file name as well. Yeah, so this is the original signal, and let's copy the file name and paste it here. And there's you need apostrophe, and uh, and then if you check the let's copy this and paste. Then you need to import Librosa. Import Librosa. Takes a while. And signal sample rate is Librosa that load. And this time let's pass file, because the path name is path, comma, the sampling rate, maybe this time 100 and 132 maybe, and the duration, let's set it to 2. Then if you 132 times 2 is 264. So for signal shape, it should return 264. So let's check signal shape. It will be 264, 2 times 132. Is that right? 264. So let's see. So you can see it's 264 shape, and it's got 264 signal values. And if you print some of the value signal up to, maybe let's check it up to 6, then these values look like this. So this is how you do conversion from audio signal and into the digital signal. So let's move on. And so now you know how to convert the analog signal into the corresponding digital signal. You can use these signals for speech analysis, such as speech emotion recognition, which is my primary research area. And however, it is hard to analyze the raw signal. To address, we can transform the signals to represent the magnitudes for the corresponding frequencies. And Fourier transform does the job. And the formula, briefly explaining the parameter, it receives the frequency, and the further corresponding frequency, what it's trying to find out is um, the magnitude of the during the time range, and f of x returns the amplitude of the given time, and e is the Euler's number to the minus I, the imaginary number, times 2 times pi times the frequency, and this is the value of time. And you take the integral for all frequency that is in the range of real numbers. And um, above formula looks daunting, though let's understand it in qualitative way rather than being too obsessed about its quantitative implications. So let's first see how to model waves. And frequency describes the number of waves that pass a fixed place in a given amount of time. So how many cycles pass within 1 second? 1 second. So frequency is about how many cycles pass within 1 second. And sine wave with the following frequency and amplitude 1 can be defined as alpha times sine of 2 pi times f, where alpha denotes the amplitude and f denotes the frequency. And with frequency 1, this is the sine wave, and with frequency 2, the sine wave, and for frequency 3, the sine wave looks like this. And I just said cycle, and let's see why we call it as cycles. The values of cosine theta and sine theta are the corresponding values of coordinates x, y within unit vectors. So plotting values of sine theta form a circle as shown in figure 1. So if you could on what is shown here on the left, then it's gonna generate a plot like this in figure 1. So to assure yourselves, let's check the numbers. The Given angle of MP, the sine function is calculated in radians. So 180 degrees is denoted as pi, and 90 degrees is denoted as pi over 2, and 45 degrees is denoted as pi over 4. And if you look at figure 1, then this degree is 90 degrees, and this one, the root, the coordinate square root of 1 over 2 comma square root of 1 over 2 um, is the vector for angle 45 degrees. And for, as I said, the sine theta, the value of sine theta is the y coordinate of unit vector for the corresponding angle. So it should be square root of 1 over 2. And if you calculate the sine of m to the pi over 4, which is sine value of 45 degrees, then it returns 0.707, which is the value of square root of 1 over 2. And let's check another numbers. And m the sine of the sine function of m to the pi over 2, which is 90 degrees, then 90 degrees, the y value is here the coordinates is 0, 1, and the y value is 1. And if you check sine pi and the sine function of pi, then it's 180 degrees is minus 1 comma o, so the y value is should be o. And you can see this is approximately number 0. And remember that the computer, because due to the limited space of memory, cannot exactly represent the floating point numbers, so you may assume that this value is 0. And let's check this time m p dot pi 3 sine function of 3 times m p dot pi over 2, then it's 90 times 3 to 70 degrees, and it's here, and it's 0 comma minus 1, then the y value is minus 1. You can see that it's minus 1. And for 360 degrees, it's number 0 again. And for 90 degrees more, then again you come here 160, and 90 degrees more, then it rotates 90 degrees more, then it's 0, 1, then the value again is 1. So having understood how to model waves, periodic sound can be decomposed into a sum of sine waves, which all vibrate and oscillate at different frequencies. So defining a sine function, it can be defined as given with parameters amplitude and frequency. It will return y amplitude times amplitude sine of 2 times mp dot pi, and which is the sine values for one cycle, times frequency times x over SR, and x is the time domain and with sampling rate 100. So the sine function of with amplitude 0.5, 4, it looks like this, and sine function of 1.5 amplitude and frequency 6 looks like this. If you add this, it will return a sine wave looking like this. So any signal, any given signal can be decomposed into uh, sum of sine waves. And so what Fourier transform is trying to do is that it's trying to decompose the original signal into a sum of sine waves, and at each frequency try to detect the magnitude at which frequencies they are they have the highest like kind of activities. So yeah, you understand what Fourier transform does. So you can Fourier transform with FFT function as shown in right. And so FFT given signal, then it's gonna return fast Fourier transformed values. And as you can see, there's one more operation of ABS which calculates the absolute value. The reason why is because what FFT returns is a complex number. So I'll show you how to calculate absolute value of a complex number. And if you um, code, then if you check the values of FFT up to 3 elements, then you can see 0.533 blah blah plus 0.j 0.06 blah blah minus 0.379 blah blah j, and the spectrum which is the calculated absolute value calculated from the fast Fourier transform value returns floating point real numbers. So um, in mathematics, an imaginary number is denoted with the symbol I, of which the square returns -1. For example, I times I is -1 and 2I times 2I is -4. And in Python, I is represented with J. And a complex number is composed of real and imaginary numbers as -1 plus 2j. And if you -1 plus 2j times -1 plus 2j, then it's 1 minus 2j minus 2j. 2j times 2j is -4. Then it's -3 minus 4j. And the complex number in equation 1 can be represented on the Cartesian coordinates as in right figure. So the absolute value is square root of -3 to the 2 plus -4 to the 2 is which is square root of 9 plus 16. Square root of 25 is 5. So let's do it with me. And um let's um so as I said, in Python a complex number is represented with j, and let's see what j times j does. Should be oj times oj, then it's 0. And if you type 1j times 1j, then it returns -1 plus oj. Let's calculate the example. -1 plus 2j times -1 plus 2j, and it should return -3 minus 4j. And let's np.apps import numpy as np.abs absolute value of this -3 plus 4j, and it returns number 5. So moving on. Now let's visualize the Fourier transform signal first. You gotta generate the frequency domain as in right. Um, this one, the first one, line space 0,3, 10. It generates um 10 frequency 10 frequencies with maximum frequency 3. And this one generates a space with 3 frequencies at 2.5 and 5. So if you pass the spectrum that we calculated earlier, and you generate the line space with a corresponding sampling rate. And then if you plot it, then the power spectrum, you can see at which frequency it's got the highest magnitude. And if you, as you can see, at frequency around 10, the given signal has the highest magnitude. So let's do this with me. And if you go to slide 9, and because we have already calculated the signal, like if you go further, and you have calculated the signal with this reverse load function, and what we'll do is that we are gonna do Fourier transform with FFT function for the given signal. So uh, FFT is MP.FFT. Before that, let's check again the signal values. So it looks like this, and signal up to maybe signal dash shape is 264, and signal let's check it up to 5. Then it looks like this, and FFT mp.fft of signal. Then check the values of Fourier function, um, Fourier transform values. So you see these are complex numbers, so you need to transform into real numbers, into floating point numbers, real floating point numbers with by calculating each value with the absolute value. So spectrum is absolute of FFT. Then if you that's up to 3 printed, then it's transformed. And what going back to what here I have been explaining the imaginary number. So if the y this axis represent the imaginary number, and this horizontal line represent the real number, and because it's minus 3 minus 4j, it is represented as minus 3 at rear horizontal line and minus 4 in the vertical line, and it's calculating the length of these two coordinates. So going back to where we were, so what we are gonna do is that let's plot this spectrum. So we just calculated the spectrum, and let's calculate the frequency range. So f, the frequency range is MP line space o comma the sure cannot remember what the sampling rate I said. Maybe let's go up. Um, so first sampling rate, I defined it as sample rate. So let's check sample rate 132, and f is mp line space of o comma sample rate comma length of spectrum. Then let's check the values of f and see um, these are the frequency domain, and import matplotlib library.pyplot as plt.plot of f comma spectrum, and the frequency ranges will lie in the horizontal line, and the magnitudes will lie in the vertical axis. And let's just do plt show. So here, this is the power spectrum of the signal, and at this signal, it's got the highest frequency. So up to here, we've learned about what brain transform does, and the complex numbers that are returned once the signal is Fourier transformed, and how to calculate the absolute value of the complex numbers to convert them into real floating point numbers. So this is the end of today's video, and thanks for listening. Goodbye.